Welcome to my video on Introduction to Vectors, Part 3. In Parts 1 and 2 of this series, I covered what is a vector and a scalar, vector addition, vector subtraction, and the multiplication by a scalar. There'll be links to those videos in the description. In this video, I want to go over the components of a vector in 2 and 3 dimensions. We're going to now take the concept of vector from a pure geometric form to more algebraic form. So sometimes this is called algebraic vectors. So first of all, we want to look at the case where we have a two-dimensional vector on the xy plane. So here's our xy Cartesian coordinate system, and we're starting at 0. Now here's our random vector. This is just going to be a generic vector. We're going to call it f. And if we want to determine the x component of this, we project this f vector down to the x-axis, and that gives us the component of f of x. And we're going to see how to do that algebraically in just a minute. Now, if we want to get the y component of this vector, we just transfer it over to the y-axis, and this gives us f of y. So there's our vector we're actually interested in. These are the two vector components of the f and y-axis. Now let's look at the components of this vector in algebraic form. So f of x, that was the distance on the x-axis, is the x component of the vector f. F of y is equal to the y component of f onto the y-axis. Now we know from trigonometry that f of x is just equal to the length of f times the cosine of theta. F of y is equal to f sine theta. And the tangent of theta is going to be equal to the ratio of f of y divided by f of x. And that's just our basic opposite over adjacent definition of the tangent of theta. Now we can solve this equation for the angle theta is a tangent inverse of f of y over f of x. So there's our basic equations that we can use to dealing with vectors in 2 dimensions. Next, let's work an example. We've got let f have a magnitude of 300 newtons and an angle of 30. Find the f of x and f of y. So what we know is, from the relationships we just showed, f of x is equal to f times the cosine of theta. That's equal to 300 newtons times the cosine of theta, which in this case is going to be 30 degrees. Let's get rid of that and put in the cosine of 30 degrees. Now what does that equal? Now we're going to solve that equation using our scientific Desmos calculator. So we got 300 times, and we're going to do the cosine of 30. It's in degree format. That's going to give us 259.8. So the x component is 259.8, and that's units of newtons. Now we're going to go through the same procedure for the y component. So f of y is equal to f sine theta is equal to 300 times the sine of 30 degrees. Let's go back into Desmos and do that math. So now we take 300 times, in this case it's the sine of theta, and we're in the degree format. So that gives us 150. So that's equal to 150 newtons. So there's our y component. Now, we can check this, so let's do a little check of this, just to make sure we did our math okay. We know the magnitude of f is going to be equal to the square root of f of x squared plus f of y squared. Now, substituting the numbers that we just derived, we're going to get 259.8 squared plus 150 squared. Take the square root of all that. That does come out to be 300. So, check. It's always good when the problem checks. Now we want to look at the relationships of the vector in 3 dimensions. The x component now is equal to f times the cosine of theta 1. Now let's go look at this diagram here. It's a little more complicated. So now our f vector is in 3 dimensions. It has an x, y, and z component. The x component would be this here. There's the value of f of x. Projecting it onto the y-axis, that gives us f of y. Projecting onto the z-axis is going to give us z. And then we're going to look at just a minute on these angles, like theta 3 is the z, and theta 2 is equal to the f of y, and that's the angle theta 1 is the x. And we're going to see what those m and l and m in this diagram mean also. So that's what we're going to do next. We just did the f of x. Now f of y is very similar. F times the cosine of theta 2. F of z is equal to f times the cosine of theta 3. Now, just like the two-dimensional case, the magnitude of f is just the sum of the squares of the individual components. So that hasn't changed. Now we want to look at those little m, n, and n. And these are called the direction cosines. And you'll see them used in different example problems or in different texts. Some people use them, some people don't, but we're going to make sure you understand what they are. So L is equal to the cosine of theta 1. M is equal to the cosine of theta 2. And N is equal to the cosine of theta 3. Now, just putting this, let's say we want to put that back in here. So what that's going to give us is f of x is just equal to f times L. F of y is equal to f of m. And f of z is just equal to f times n. And we know from trigonometry that L squared plus m squared plus n squared is equal to 1. So this is just going to give us some more ammunition, so to speak, to handle some of these problems, because three-dimensional examples start getting a bit more complicated. Well, I hope you got something out of this video, learned something, and if you did, like and subscribe to my channel, and thank you for watching.